Hi everyone, thanks for coming to the Adventures of a Python Script. My name is Dema, and I'm a fourth-year software engineering student at the University of Guelph, which is a small university near Toronto in Canada. I'm also one of the organizers for Bang Bang Con West, which is a West Coast sister conference of Bang Bang Con here in New York. So I have a URL, and if you go to that URL, you'll have the slides for this talk and a few resources that helped me write this talk. Let's hop in. So let's talk about Python interpreters. There's actually quite a few, and I'm going to introduce a few and talk about what makes them so different. There's stackless Python, which is the Python interpreter that doesn't use the stack. Instead, it uses the heap. And the cool thing about this one is that you can have these tiny tasks called tasklets, and you can run them, and you can run a bunch in a thread. So it's great for microthreading. You can have, there's also Python, which is the Java implementation of Python. And Java programs can interact with Java packages and vice versa. And so if you wanted to write something that uses Java package, but in Python syntax, and it will help you in write it faster. And when I was interning at IBM last summer, we used Python to package and deploy WebSphere applications onto the server. It was pretty great. Then there's IronPython, which is similar to Python, but that uses the .NET languages. And so you could do the same thing, .NET to IronPython and IronPython to .NET. Then we have PyPy, which is the Python interpreter written in Python. And it's known for being fast, utilizing memory better, and it also is stackless, so you can do massive microthreading, the same way stackless Python can do. And finally, we have CPython. As you can tell by its name, it's written in C, and it's the official implementation of Python. And for the rest of this talk, we're just going to be focusing on how CPython works, since it's the original one. So how does CPython work? So if we look at this snippet, we have hello PyGotham, and it prints hello PyGotham, and then we call that function. And so the first thing that happens is that we will tokenize the code into a series of tokens. And so you'll have three columns, one that will have the line number and the character number, and then in the middle column we will have the characterization of what the token represents, and it's pretty vague. You mostly have name for like any other string other than like left parentheses or like new line or like the indentations. And then the third one is the actual string format of what the token is. And so taking all that, we get to generate the parser tree. And the parser tree looks like this in a raw nested list format, and that doesn't really mean much to us right now, but the numbers get mapped to macros in C. So 257 would be like file input, and 263 would be like function definition. And so if we take this all and we map it to a tree looking like graph, we will get this. And converting all the numbers to the things they map, we get something that makes more sense to us. We have the file input, a statement, parameters. You can kind of tell what the program does looking at this. So the parser tree has some responsibilities, and it does syntax analysis. So if you had an indentation error, or you write printf thinking you're writing C, but you're actually writing Python, it will say syntax error, invalid syntax, and the process will stop at here. But if you have valid syntax and everything's great, we get to go to another tree, the abstract syntax tree. And by the name, you can tell that the abstract syntax tree is a more abstracted version of this tree. And by looking at it as well, you can tell that it's pretty simple: module, function def, parameters. Yeah. And so the abstract syntax tree also has responsibilities. And it checks for things that are syntactically correct, but logically do not make sense. So our function doesn't take an argument. And if you were to pass an argument to our function, it would tell you type error. PyGotham takes no arguments, but you gave it one. And the process will stop here, as per usual. After that, we're done with trees, and now we go to graphs. Kind of like trees. And so we have the control flow graph. And the control flow graph kind of shows the flow of our program. And so every function kind of gets its own box, because functions don't necessarily need to be called. And so our program is pretty simple. We have hello PyGotham gets called, and then the print function gets called, and then we just get a print statement. But if we had something more complicated, like the Fibonacci sequence, and this is what the source code would look like, and it would map to something like this. And so you can see that the arrows can go all over, and you really can just loop through a bunch of things. And so the control flow graph just has a few rules. As long as it has one point of entry and one point of exit, you can have multiple routes between. And this step is usually the last step before bytecode, so if you got to this point, your code probably runs. So now we have bytecode generation. And the bytecode kind of looks like the tokenizers, except the middle, instead of having the categories of what the tokens are, we have the actual opcode. And so this is the bytecode that our example looks like. So the final steps, as you can tell by the bytecode, there was like a pop line. So the final steps is that the code gets executed on a stack-oriented virtual machine. So they just get pushed and popped, and that's how things work. So now that we learned a lot about, or a little, about how CPython works, let's get to the abstract syntax tree. So we talked about it a little. It's not a concrete representation of the original source code, but it's an abstraction that discards the details and focuses on the syntactic structure. So why is it useful? I mean, if you wanted to contribute to CPython, understanding how this all works is probably helpful. And you could also use it to, kind of build linters and debuggers, which is great. So let's look at a linting example. How many here are familiar with pylint? You can raise your hand. Yeah, all of us. It's great. So you can write 3 different types of checkers by yourself if you think that the pylint functionality doesn't cover all your use cases. So you can do a raw checker, which analyzes the raw file stream. You could also do a token checker that analyzes the tokens, as we've seen in the first step in the compilation process. And you can also write an AST checker, which analyzes the abstract syntax tree. So we're going to do an abstract syntax tree checker example. And so pylint doesn't actually use the AST module that Python has. It uses the Asteroid module. So it's basically the AST module plus some more functionality to really help you. So our example will be, we want to write a checker that looks at the ordering of import statements. And it wants to make sure that they're alphabetical and the import statements go before the from import statements. And yeah. So just to touch base on what a correct example is we have import statement before from import statements. And if you look at the from Django DB modules, C comes before the letter F. So everything's good. And then this is just an example of an incorrect statement. If you have a from OS import path before the import OS one, it would flag as an incorrect. And then we talked about Asteroid, but a small example of Asteroid is that it works pretty similar to the AST module. So if we import it and we put our function into a string and then we just call it to get parsed, it would print something easily readable, kind of like this. And so you can kind of see that it tells you things about the name, the doc, the file, if it's written in pure Python. And then it also gives you the body, which is what our hello_pygotham body is. And so Pylint gives you some boilerplate code that you can get started with to write your actual thing. So first, it wants you to really name what your checker is going to be called. So we named our class alphabetically sorted imports, and it implements asteroid checker. And so we also name it to actually get it in the Pylint as alphabetically sorted imports checker. And that's our new rule. And then these next 3 variables are just variables we're going to use for printing and for kind of comparison when we actually want to compare if our import statements are alphabetical or not. And so we're at the message part. And this message part is what happens if the rule gets triggered or flagged. And so there's actually rules of how to write a message. And the first thing, C5001, is the ID of your message. And so there's actually convention. So it has to be 5 digits. And the first character has to be either C for convention, W for warning, E for error, F for fatal, or R for refactoring. And the last 4 digits can be anything as long as you don't have the same message ID twice. And then the second part is the actual message that gets printed to the user, which is the display message. And then you have the message symbol. For us, it's unsorted import from, and that would be an alias to the message ID. And then we have the message help. So in case the user's like, oh, why did I get this message? Then they can go pylint -- help with the message. We also have the option to have an option, which is a user configurable option. And then there's also a priority. So it depends how much you think this rule that we're creating is a priority. And it has to be lower than 0, so it has to be a negative integer. And it will kind of, the more negative, the more priority this rule is. So the actual implementation of the rule. So there's a function called visit import from node. And the node is just basically a 2-element that has the object name and its alias. And it can have no alias if that doesn't exist. And so we want to take all the nodes and we want to sort them. And that's how we know that we can compare them to each other to see if they're actually alphabetically sorted or not. And so here, we are actually just checking if this rule violates or not. So we're just doing a check if the actual index that we got and the index that we are matching it to is correct or not. And if it is, we will add it to the message so that we can emit it to the user saying like this, this import statement needs to be before or after this one. And that's how Python works. And then we can also use the AST to help us with debugging. So there's a really cool open source project called Birdseye. And it uses the AST to check if your check and breakpoint through your code to see the visual and the graphical debugging. And yeah. So our example doesn't really work if you wanted to show how Birdseye works. So I just made a function that has a bunch of variables, multiplies, and then checks a conditional. And then so all you have to do is just add the eye decorator to Birdseye. And then when you run Birdseye, it'll give you a website. And then you can see all the Python files. So Dema.py is my Python file. And the 2 functions that have the Birdseye decorator. And then you can click on that. And then you can see and kind of click through the different steps of your code. And it will show you what each variable is at a specific point. And this is great if you're new to Python and you don't really want to use a real debugger for yeah. And then you can also check the conditional statements. So we can check that at x is greater than y is false. And so Birdseye, if you don't want to use the actual website, it actually has integrations with VS Code, Jupyter Notebooks, and you can even it also has a PyCharm plugin. So yeah, thank you.